Welcome back to AI.Code.Cast. We love to dive deep into some really cool coding challenges, and today we've got one that's a bit of a head-scratcher. It's called minimum remove to make valid parentheses.
Yeah, this is a classic problem. It seems pretty simple on the surface, but it can be tricky.
You're telling me, so imagine you've got this string and a bunch of letters and parentheses mixed up like a messy line of code, and the problem is that some of those parentheses are just in the wrong spot.
Right.
And the goal here is to find out which parentheses to remove, as few as possible,
Yeah.
of course, so that what we're left with is a perfectly balanced string.
Yeah, and this isn't just some theoretical problem either. Think of it. You use parentheses all the time when you're coding, like in math expressions, function calls, even code blocks.
Right.
They got to be in the right place for your code to even compile, let alone run without errors.
Absolutely. So where do we even start with something like this?
Well, I always tell people to begin with the simplest approach, even if it's not the most efficient. You know what I mean? What do you think would be the most straightforward, like a brute force way to solve this?
Hmm. Well, if I was just going to try everything to see what worked, I guess I'd start by removing just one parenthesis at a time and then checking if the string is valid. And if it's not, I'd try taking out two parentheses, then three, and so on, just trying every single combination.
Exactly. You got it. That's the brute force method in a nutshell. Just try every possibility until you find something that works. But what's the catch here? What's the problem with that?
It just seems really inefficient, especially if the string is super long. Trying every combination would take like forever.
You nailed it. The time complexity of this brute force approach, it's exponential, which is not what we want when we're trying to write good optimized code. So how can we do this better? Got to be a smarter way.
There's got to be. We need a way to find the right parentheses to remove without testing every single option. What if we could keep track of which parentheses are open, like waiting for their closing match?
You're on the right track. That's a really clever idea. And it leads us to a way more efficient approach using a data structure called a stack.
A stack, like a stack of pancakes.
Perfect analogy. Think
Right.
about it. You can only put a pancake on top of the stack or take one off the top right. It's what we call last in, first out, or LIFO.
Okay, I see that. But how does a stack of pancakes help us with parentheses?
Well, remember how parentheses work? Every opening parenthesis is waiting for its closing buddy to show up later down the line. And the last opening parentheses you see needs to be the first one to be closed. That's that LIFO principle in action.
Oh, I think I'm starting to get it. So as we go through the string, we could use a stack to keep track of all the opening parentheses that are still waiting to be matched with a closing parenthesis.
Exactly. So every time we see an opening parenthesis, we push it onto the stack. And when we hit a closing parenthesis, we need to do a quick check.
We check if the stack is empty. If it is, then that closing parenthesis doesn't have a match, so it's got to be invalid.
You got it. And if the stack isn't empty,
Then we pop the top element off the stack, which is the last opening parenthesis we saw. That means we've found a match.
that's it. You're a natural at this. But what if we get to the end of the string and there are still parentheses left in the stack?
Well, those must be opening parentheses that never got their closing match, so they need to be removed.
Precisely. So this stack-based approach helps us deal with both those bad closing parentheses and unmatched opening parentheses really smoothly. But I bet you're already thinking about how to make this even better. What's going through that coding brain of yours?
Uh-huh. You know me so well. This stack approach is really cool. But I can't help but wonder if we could do the same thing without using an external data structure like a stack. Is there a way to work directly with the string itself, maybe?
I knew you'd ask that. And luckily for us, there's a very clever solution that does exactly that. We'll talk about that after this quick break.
Welcome back to AI.Code.Cast. Before the break, we were just starting to talk about solving this parenthesis problem without using a stack.
Right. And this approach we're going to look at now is all about working directly with the string itself and removing those extra parentheses in a couple of well-planned steps.
Sounds good. I like a good plan. Tell me more.
Okay, so picture this. We're going to make two passes through our string. The first pass is all about getting rid of all the bad closing parentheses, and we can do that by keeping track of what we'll call a balance counter.
A balance counter. Interesting. How does that work?
It's pretty straightforward. We start with the balance at 0, and as we go through the string, every time we see an opening parenthesis, we increase the counter by 1. It's like we're opening up a new level, you know? And when we hit a closing parenthesis,
We decrease the counter by 1, right? Like we're closing that level back up.
exactly. So that balance counter is telling us how many open parentheses we have at any point in the string. Now, what happens if that counter ever dips below 0?
That means we've hit a closing parentheses, but we haven't seen enough opening parentheses to match it right, like trying to close a door that was never open.
That's a great way to put it. So if that balance goes negative, that closing parentheses is definitely invalid and we got to get rid of it.
Got it. So after the first pass, we've taken care of all the closing parentheses that are clearly in the wrong place. But how do we deal with the opening parentheses that might be messing things up?
That's where our second pass comes in. And this is where things get kind of clever. Instead of just going through the string again, we're going to do a little trick.
Oh, I like tricks. What's the plan?
We're going to reverse the whole string and switch the roles of the opening and closing parentheses.
Wait, reverse and swap. Whoa, let's slow down for a second. Imagine what this looks like. Say we have the string after that first pass. What would it look like after we reverse it and swap the parentheses?
Perfect example. Reversing that would give us EOCE, and then swapping the parentheses would make it EOCE. Now think about what just happened.
Whoa. The bad opening parentheses in the original string are now bad closing parentheses in this reversed and swapped version. It's like we're looking at the problem in a mirror.
You got it. And now we can just do the same thing we did in the first pass, but on this mirrored string. We'll be removing the bad closing parentheses, which were actually those pesky opening parentheses all along.
So we go through the whole process again, tracking the balance, removing the problem parentheses, and then when we're done.
We reverse the string back to how it was originally and switch the parentheses back to their normal roles.
And just like that, we've cleaned up both the bad closing and bad opening parentheses in only 2 passes. And the best part is we didn't even need to use a stack at all.
Exactly. This two-pass method is really efficient in terms of both time and space complexity. It's still ON, just like the stack method. So there can be more than one good way to get to that optimal solution.
This is mind-blowing. We've got 2 different methods, both with that awesome ON complexity, but they solve the problem in completely different ways. It's amazing. What are the pros and cons of each method? How should a programmer choose which one to use?
It's a great question, and often it comes down to what's most important for your code. Sometimes you want to make sure it's easy to understand, and other times you might need to prioritize making the code as short and efficient as possible. What are your thoughts?
If I was working with a team and I wanted to make sure everyone could easily follow the logic, I think I'd go with the stack approach. It feels more intuitive to me, like it reflects how parentheses actually work in code.
You're right that stack approach is a great choice if readability is your top priority. But what if you were working on a project where speed was really crucial and you were comfortable working with strings in a more abstract way?
Then the 2-pass method, with that clever reversing trick, might be the best option.
Yeah,
It's like we outsmarted the problem by thinking about it in reverse.
exactly. It all depends on the situation. But you know what? There's actually an even more efficient solution out there. It's pretty amazing.
More efficient than this, I'm not sure my brain can handle it.
It's a little tricky to wrap your head around, but it's super efficient. We can actually solve this whole problem using just one integer variable to keep track of the balance, no stacks or string reversals needed. Pretty cool, huh?
You definitely have my attention. Tell me everything. Welcome back to AI.Code.Cast. We've been talking about this minimum remove to make valid parentheses problem, and we've already found some really clever ways to solve it, but you mentioned an even more efficient approach. I'm dying to hear about it.
So this method is all about efficiency and keeping things simple. Imagine solving this whole thing using just one integer variable to keep track of the balance. No stacks, no reversing strings, or anything like that.
Whoa, hold on, just one integer. How does that even work?
It all comes down to understanding how those opening and closing parentheses work together. Remember in that 2-pass method, we talked about how we kept track of the balance as we went through the string?
Yeah, we increased the counter for opening parentheses and decreased it for closing ones.
Exactly. Well, the streamline method does something a little different in that first pass. Instead of removing those bad closing parentheses right away, we just mark them as invalid.
So we're not actually changing the string in that first pass, just making a note of which closing parentheses are causing problems.
You got it. We're gathering information. And here's the cool part. By the end of that first pass, we know exactly how many closing parentheses are messing things up, and that tells us exactly how many opening parentheses we need to remove to make everything balanced again.
Wait a minute, how can we figure that out? Just from the bad closing parentheses.
Think about it. For a string to be valid, the number of opening parentheses has to be the same as the number of closing parentheses, right? So if we know how many closing parentheses are causing an imbalance, we can figure out how many opening parentheses need to go to make things even.
That's brilliant. So we don't even need to look for those bad opening parentheses in the first pass. We just know they're there. But how do we know which opening parentheses to remove in the second pass?
That's where it gets interesting. In the second pass, we go through the string backwards from right to left and start removing those bad opening parentheses, but only from the rightmost end of the string.
Why from right to left? What's the logic there?
Removing those opening parentheses from the right side gives the remaining opening parentheses on the left the best chance of finding their matching closing partners. It's like we're clearing a path for them.
I see. Can you give me an example?
Sure, let's take a simple string like
Right.
after the first pass, we see that all the closing parentheses are valid, the balance is 0, so we don't need to remove any opening parentheses in the second pass. It's already balanced.
Okay, that makes sense. What about a more complicated example like,
Great example. In this case, after the first pass, we'd see that that very last closing parenthesis is the problem. The balance would be +1 at the end because of that extra open parenthesis at the end.
so we know we need to get rid of one opening parentheses, but why from the right side?
We'll think about what would happen if we removed one of the opening parentheses from the left side. That would actually make the imbalance even worse. It's like we're making a bigger gap. But if we remove that last opening parenthesis on the right, then that final closing parenthesis now has a matching opening parenthesis and the string becomes balanced.
Okay, now I get it. Removing from the right side gives those other opening parentheses the best shot at finding their matches. So we just keep removing bad opening parentheses from the right until we've removed as many as we figured out we needed to in that first pass.
Exactly. And what do we end up with? A perfectly balanced string. We've removed the fewest parentheses possible, and we did it all in just 2 passes, and all we needed was one little integer variable to keep track of everything.
This is incredible. 3 different ways to solve the same problem, each one with its own unique logic and advantages and disadvantages. It's like a lesson in how to think like a programmer.
And the best part is that these ideas aren't just for parentheses. You can use them in all sorts of situations where you're dealing with balanced structures like brackets and arrays, braces and code blocks, even tags in HTML. It's all connected.
This has been an amazing deep dive. I'm feeling so inspired by the power of clever algorithms, and I have a whole new appreciation for those little parentheses.
Don't forget how important it is to start simple and then refine your approach step by step, and never underestimate the power of a well-placed integer.
Thanks for joining us on AI.Code.Cast, and until next time, happy coding.